Have you ever stopped to think about what a rocket launching into space, a car slamming on its brakes, and an apple falling from a tree all have in common? Well, it turns out it's a single, fundamental concept that rules over how everything moves, and that concept is acceleration. So let's dive in and break it down.
So really, what is the connection between a sprinter exploding from the blocks, a car coming to a stop, and an apple dropping to the ground? On the surface, they seem like totally different things, right? But they're all playing by the exact same rule of physics. The hint is in how their motion is changing. If you were thinking acceleration, you nailed it. But here's the thing that trips a lot of people up. Acceleration isn't just about speeding up. That car hitting the brakes, it's accelerating too. How can that be? Well, it's because acceleration in physics is any change in how something is moving.
To really wrap our heads around acceleration, we first have to talk about its partner in crime, velocity. You can't really have one without the other. They're two sides of the same coin when it comes to motion.
Okay, so here's the official sciencey definition. It sounds a little formal, but the key phrase to lock onto is change of velocity. Now, velocity isn't just about how fast you're going, that's speed. Velocity is speed times in a specific direction. So you're accelerating anytime you change your speed, or your direction, or even both at the same time.
Let's make that even simpler. For a second, let's just focus on the speed part. At its heart, acceleration is just a measure of how quickly your speed is changing. Are you flooring it in a sports car? That's a massive, sudden change in speed. That's high acceleration. Are you just gently coasting to a stop sign? That's a slow change, so it's low acceleration. It's all about how fast the change happens.
Now, of course, science loves to put numbers on things. It's not enough to say something is fast or slow. So how do we actually measure acceleration? Well, thankfully, there's a really elegant and simple equation for it.
And there it is. Now don't let the symbols intimidate you. This is one of the most useful little equations in all of physics. It reads A for acceleration is equal to delta V divided by delta T.
So what's up with those little triangles? Well, that's the Greek letter delta. And in math and science, it's just a handy shortcut that means the change in. So delta V is simply the change in your velocity, and delta T is the change in time, or how long it took for that change to happen. See? Pretty straightforward.
So let's use this in a real-world scenario. Imagine a car is at a stoplight, so its initial velocity is 0. The light turns green, and 6 seconds later it's going 60 miles per hour. Step 1, the change in velocity is 60 minus 0, which is 60. Step 2, the time was 6 seconds. Step 3, you just divide 60 by 6 and you get an acceleration of 10 miles per hour per second. It's that easy.
But what if you don't have all the numbers? Sometimes the best way to understand motion is to actually see it. And this is where graphs become an incredibly powerful tool for visualizing what acceleration is doing. When you're looking at a graph that plots speed versus time, the whole story of acceleration is right there in the slope of the line. A really steep line means the speed is changing very quickly, so that's high acceleration. A shallow, gentle slope means low acceleration. It's all about the steepness.
And this shows us the two main flavors. On the left, that perfectly straight, sloped line tells you the speed is increasing at a steady, constant rate. Think of a ball rolling down a smooth ramp. But over on the right, that curved line means the acceleration itself is changing. That's like being in a car and pressing the gas pedal down harder and harder and harder.
Okay, quick pop quiz. Let's say you're on the highway with cruise control set at a perfect, steady 60 miles per hour. Your speed isn't changing at all. So what is your acceleration? And what would that line look like on our speed time graph?
And the answer is a big fat 0. If your speed isn't changing, then the change in velocity is 0. And on the graph, that would look like a perfectly flat horizontal line. A slope of 0 means, you guessed it, 0 acceleration.
Okay, so we've got a good handle on speeding up, but what about the other side of things, slowing down? We've already said a braking car is technically accelerating, but there's a more common, specific word we use for that.
And that word is deceleration. In the world of physics, it's really just a negative acceleration. The math still works out perfectly. If you're slowing down, your final velocity is less than your initial one, so when you calculate the change, you just get a negative number.
The car analogy is just perfect for this. Hitting the gas pedal gives you a positive acceleration. Hitting the brake pedal gives you a negative acceleration, or deceleration. It's the same physical concept, just happening in the opposite direction.
Now for our final topic. where we get to see all these ideas, acceleration, changing acceleration, balanced forces, come together in one of the most common things we see every day, falling objects.
It's a classic physics question, isn't it? We all know intuitively that a feather flutters down slowly while a hammer just plummets. But why? Gravity is pulling on both of them. The answer has to do with a second, opposing force that messes with their acceleration.
This is what's so wild. If you were on the moon, in a vacuum, with no air, that feather and hammer would fall at the exact same rate and hit the ground at the same time. But here on Earth, we have an atmosphere, and that air creates resistance, an upward push that works against gravity. That push has a huge effect on a light, wide object like a feather, but not so much on a dense, heavy hammer.
And all this leads to a really cool concept called terminal velocity. So, as something falls, gravity makes it speed up. But the faster it goes, the stronger that upward push of air resistance becomes. Eventually, if it falls for long enough, it reaches a point where the upward push of the air becomes exactly as strong as the downward pull of gravity.
At that exact moment, when those two forces are perfectly balanced, the object's acceleration drops to zero. It stops getting faster. It's still falling, of course, but now it's at a constant maximum speed. That speed is its terminal velocity.
So I'll leave you with a final thought to chew on. Think about a skydiver. When they shift their body from a flat, spread eagle position to a streamlined head-first dive, what are they actually doing? They're changing their shape to reduce air resistance. So how does that shift the balance of forces, and what does it do to their terminal velocity? It's a perfect real-world example of taking control of acceleration.